Hi everyone, Mr. Smith here, and in this video lesson, we're going to talk about the magnetic force on a moving charge. So let's get started. If you're taking this class in summer school with me, it's my hope that you would have watched the 15-minute excerpt from the NOVA documentary Einstein's Big Idea that focused on Michael Faraday. Not only is it just like entertaining and you learn a lot of history and the visuals are great, but hopefully it also reviewed some topics you learned in the grade 11 course. Specifically, hopefully we're all convinced the moving charge in a magnetic field experiences a force. So the I believe most famous and visually intriguing illustration from that video excerpt was this experiment that Faraday performed. So he had a magnet sitting in mercury, and so this was creating a magnetic field, and had a wire suspended around this magnet. And when he turned on the wire, when a whole bunch of charges, the current flowed through this wire, the wire began to spin around the magnet. And this only happened when the switch was on and when the charges were moving. So moving charges experience a force. And again, hopefully we're all convinced of that. Hopefully you guys all did learn that in your grade 11 physics course. As I shoot this video, I know a lot of students in their last semester might have had their semester kind of cut short and then went online and maybe didn't get to go into this as much. But I hope our starting point is, and hopefully we're all convinced, a moving charge in a magnetic field will experience a force. And in this lesson, we want to actually quantify what that force is on a single moving charge. Later, we'll talk about the force on a whole bunch of moving charges in a wire or a conductor. So as we've seen, a current can exert a force on a magnet. And then what we're kind of looking at right now is a magnetic field can exert a force on a current or moving charges. So we're going to describe the factors that affect this force and then get an equation for the force. So the magnitude of this magnetic force, and we'll call it Fm on a charged particle. So it's directly proportional to three things. It's proportional to how strong the magnetic field is. So loosely speaking, if you double the strength of a magnet and the magnetic field, you would double this force on the charge. What's interesting is that the force a charge experiences is actually directly proportional to its velocity, how fast it's going. So if you double the speed of a charged particle, it experiences twice the force. That's pretty cool in a magnetic field. And it also depends on the charge of the particle. And because it's directly proportional, if you double the charge in this magnetic field, that charge would experience double the force. So it's directly proportional to these things. It also depends on the angle between the magnetic field and the velocity vector. So that means if you have, say, on our diagram here, you have some uniform magnetic field pointing left to right. It depends on, if you're in this first illustration here, let's say we have a charged particle Q, and it's moving parallel to the magnetic field. It's going to experience a different force than the same charged particle moving perpendicular to the field. And this is where we're going to talk about that difference. So I think I need to get something that shows up. So go to yellow. So it turns out that Fm is a minimum when the magnetic field and V are parallel. And a minimum meaning that the charge won't actually even experience a force. It'll be zero. So in this first case, where a charge moves parallel to the magnetic field lines, that charge will not experience a force. It's just going to keep moving according to, whatever its initial motion was. If it's in a straight line, it's going to continue in a straight line. It's not going to experience any force at all. And Fm is a maximum. Is a maximum when B and V are perpendicular. So it's those cases where you have a magnetic field and your charge is moving perpendicular to that magnetic field where you're going to experience a force. And everywhere in between, the force goes from 0 to some maximum, but it's a maximum at this point. So that's pretty interesting too. So this Fm depends on 4 things. It depends on the magnetic field strength, depends on the speed of the charged particle, depends on its charge, and also the angle between B and V affects it too. So we're going to put all that together. So I might just add, just in this diagram, Fm would be 0 newtons. And I'm just going to put here, Fm is a maximum. But we still haven't really quantified like how to calculate that, right? So let's put it all together. So we said it's directly proportional. This magnetic force is directly proportional to 3 things: the charge, the speed, and the strength of the magnetic field. Now, this is magnitude. So as usual, when we're talking about magnitude, we're plugging in positive values for Q. So if the charge is negative, we're still going to plug in a positive. It's the magnitude of charge. Q times V times B. Now, how do we address the angle? So do you guys know a function that is 0 when the angle between that is 0 for an angle of 0 degrees? So that would be, if the velocity vector and magnetic field are parallel, the angle between them would be 0. And when they're perpendicular, the angle would be 90. Do you guys know a function that's 0 at 0 degrees and is a maximum when theta is 90 degrees? And if you think back to your grade 11 math course, the function that satisfies that property is the sine function. So that's the last piece of info in this equation, sine theta. So that when you plug in theta equals 0, you get 0. And when you plug in theta equals 90, you get 1. And you get the maximum possible force. So that's the equation for the force that a moving charge would experience in submagnetic field. So just to summarize what all these things mean. So Fm is the magnitude of the force. We'll talk about direction in a second. Q is the magnitude of charge. V is the speed of the particle. Say speed of the charged particle. B is the magnitude of the magnetic field strength. Now this is a new variable, magnitude of the magnetic field, magnetic. That's funny, mix those up. Magnetic field strength. Now this is a new variable and it has a new unit. So right now, I'm just going to tell you what that unit is. And it might not be till after a future lesson where we have a really actually a solid understanding of how we can interpret this unit. But the units of magnetic field strength you may have heard before is the Tesla. And we use the symbol T for that. So right now we'll just use it, and then later on, when we talk about the force on a conductor, we'll actually have a way of wrapping our minds around what a Tesla is equivalent to. But for now, we'll just units for the Tesla. And finally, theta is the angle between the magnetic field, and the velocity vector. All right. So that takes care of the magnitude. What about the direction? So let's talk about the direction now. So as I said, that equation we just talked about specifies the magnitude of force, but not the direction. So let's talk about the direction right now. So consider a plane parallel to the magnetic field B. And so you can imagine if you take your right hand, imagine your right hand is the that plane parallel to the magnetic field and the velocity, with your fingers pointing to the your fingers pointing in the direction of the magnetic field, and your thumb pointing in the direction of the velocity vector. So in this diagram here, yellow, or I think I'm yellow. I want to be dark. This diagram has a symbol for current or moving positive charge. We'll do that later, but your thumb is the direction of the velocity. The direction of that the charge would feel would point straight out of your palm. So if your thumb is in the direction of motion of a positive charge, so this right hand rule is for positive charge. Again, thumb, the direction of the positive charge. Your fingers are the magnetic field. Your palm tells you the direction of the magnetic force. So you can see in this diagram, with the thumb pointing to the right like this and B pointing like so, in this diagram, using this person's right hand, the magnetic force would be pointing up out of this person's palm. Now, again, this right hand rule is for a positive charge. What this means for a negative charge, the negative, I don't know why I use my mouse for that. A negative charge would experience a force down. So this right hand rule for the direction, where's my cursor? There it is. Fm for a negative charge. Some people, if they're doing a negative charge, just like to use their left hand, and that works. But I prefer this right hand rule. This right hand rule is for a positive charge. And then I just imagine if it's a negative charge, then the force would just be out the back of my hand. So this right hand rule, people who have taken calculus might be familiar with right hand rules because you've learned the cross product. Calculus people would actually hopefully look at the equation for the force on a moving charge and actually recognize that as the cross product. The magnetic force is equal to the charge times the velocity vector crossed with the magnetic field. Now, if you haven't taken calculus, that's okay. All you need to know is here's how to get the magnitude of charge. Fm equals QVB sine theta. And you will, and actually this is true for everybody, you need to get a bit of practice just thinking about the direction of the magnetic force, because it is kind of like a 3D idea. And admittedly, it does take a bit of getting used to. Here's some illustrations, which hopefully kind of cement the idea of the right-hand rule for you. So let's look at this first diagram in diagram A. So imagine this charged particle is moving up like so. Let's imagine, so let's practice using this right-hand rule. Can you stick your fingers in the direction of the magnetic field and your thumb in the direction of the object's motion? Your palm will point towards the direction of the magnetic field. So if you want to pause the video, think about that. Which direction would the magnetic field be pointing? So I'm going to do it here. So this I have my right hand here. So I'll flip for you guys. So for me, I'm seeing the magnetic field is pointing left on my page, and my thumb is pointing up on my page. So the direction of the magnetic force is going to be towards me, out of the page, out of the screen. So if you're looking at a page, it's out of the page. And if you're watching the screen like me, it's out of the screen. At least at this position here, that maybe I'll call position A. And if you guys can imagine, do I want to do this? Yeah, why not? So look at this path of this. This is kind of implying the direction this charged particle is going to take. So what kind of motion do you guys know where the force and acceleration is perpendicular to the path of motion? And the diagrams here kind of give it away. But if you said uniform circular motion, then you'd be right. And actually, in a uniform magnetic field like this, the motion of a charged particle is going to be ideally circular, which is pretty cool. Because think about at another point B. So let's think about at the top of this circular motion. And at the top, the V is going to be out of our page. So at point B, the magnetic field is going to the left. And if you put your thumb pointing out of your screen or out of your page, your palm is pointing down. The magnetic force would be down on our page, which is consistent with the uniform circular motion there. Is down on the page or screen. So again, this is going to take this right-hand rule. It does take some getting used to, especially for people that have never used a right-hand rule before. But yeah, here's this second illustration illustrating a right-hand rule 4 different times. You can see the magnetic field is going down, and we have the velocity at several different spots, and the magnetic force is perpendicular to both V and B, and obeying a right-hand rule. And so if you want to just convince yourself with those 4 different spots, the right-hand rule holds, and each time the magnetic force is towards the center of that circle. Now, that doesn't mean that a charged particle will just always travel in a circle. If that charged particle, say, was moving at a constant speed already, now it might move in a constant horizontal speed, but move in a circle through this magnetic field, and you might see some motion, kind of like a corkscrew motion. Or if it was accelerating to the right, then what you might see is this corkscrew motion, but as accelerating, these corkscrews get more pronounced and more pronounced and more pronounced. But generally, a charged particle in a magnetic field you're gonna tell it's in a magnetic field. It's gonna have some circular motion, and you can tell if it's gonna be an electric field because it's gonna have some, like the second example, it's gonna have some kind of linear acceleration. So that's a way to tell between the two. Magnetic field, circular. Electric field, you're going to have some linear acceleration. All right. Let's do an example. Just again, applying the right-hand rule. So with the problems I'm giving you guys, and generally with most resources use this idea. Because we're doing a 3D idea, and most of all your practice lessons and stuff is on a 2D piece of paper, right? So how can we illustrate that, this 3D idea in a 2D piece of paper? So here you see these X's. They're indicating the direction of the magnetic field. And the question says that the magnetic field is directed into the page. So I'm going to say, think of B as an arrow. Like a little arrow, like Hunger Games, with little fletching on the back. So if this arrow was going into the page, what would you see? Well, you'd see the back of it, right? And the back of an arrow, you'd see the fletching, the feathers, and it would look kind of like that. That's into page. If it was coming out of the page, what would you see? Well, you'd see the arrowhead, right? So you'd see a point and then the arrowhead, and this is what it would look like out of page. So if you have a diagram like this, you just know X is into the page, open circle with the dot, out of page, and think of it as which way an arrow would be traveling. So we have an electron. So we know the charge in an electron, and it accelerates from rest in an electric field through a potential difference of 46 volts. So we're going to tie in some stuff from our previous day that's going to tell us what new speed this electron reaches. So we'll know our V. The electron then leaves the electric field and enters this magnetic field with the magnitude 0.2 teslas, so that's B, and it's directed into the page. So we'll know Q, we'll know V, we'll know B, and we'll talk about the angle, and then we'll tie in some circular motion. So this question has it all. It's going to be great. So let's find, first of all, let's do A. So let's find the initial speed of the electron entering the magnetic field. So remember, in an electric field, the change in electric potential energy is going to be converted to kinetic energy. So electric potential energy lost is equal to kinetic energy gained. So this is a concept we went over in the motion of charged particles in an electric field lesson. Inside a uniform electric field, and actually this is just true all the time, the change in electric potential energy is given by this charge times the change in electric potential. And if our electron was originally at rest, then the change in kinetic energy is just 1/2 mv squared. It's the kinetic energy that it leaves the electric field with. In our case, Q, I'm just going to throw this in. Q is actually, it's an electron, right? So the charge in an electron is negative, and it has the elementary charge E. And that allows us to find V. So we'll get those will be positive 2 times E times delta V divided by the mass. Again, E is a constant, it's positive, the elementary charge. The charge of an electron is negative E, the charge of a proton is positive E. But let's calculate that. So 2 times 1.6 times 10 to the minus 19. The voltage was 46. And electron mass. Now, this is actually something we'll talk about later, how the mass was determined. But for now, this is something we can look up. It's 9.1 times 10 to the minus 31 kilograms, or at least I think it is. Yep. So 2 times 1. Oh, and don't forget to, I was naughty there. That would be square rooted, right? Yeah. Let's bang this out. All right, so I got about I got basically 4 times 10 to the 6, I think. Yep, 10 to the 6 meters per second, so pretty fast. All right, so tying a little bit of stuff from a previous day. So that's actually a bit of review. Now let's go to part B. Now that we know the speed that it goes in that electric field with, or that magnetic field, we can find the magnitude of the force, and then we'll talk about its direction afterwards. So Fm equals Q, V, B, sine theta. All right, so Q, this is the, and then remember, this is magnitude, right? So the magnitude of our charge, it's an electron. The magnitude of that charge is 1.6 times 10 to the minus 19. V, we just found, 4 times 10 to the 6. The field strength, 0.2 teslas. Now, what's the angle? Our diagram indicates that the electron is moving right on our page, and the magnetic field is going into our page. The angle would be 90 degrees. And we can calculate that. Times 4x6 times 0.2. So I got 1.3 times 10 to the minus 13 newtons. So that's the size of our magnetic force. Now, what's the direction? So can you guys apply the right-hand rule? Let's imagine, so apply the right-hand rule, maybe even pause the video. Think about the direction that this electron would experience a force. So if you want to pause and unpause when you're ready. All right, so fingers in the direction of the magnetic field into your page. Thumb in the direction of the speed, that's to the right. So I'm going into my screen and going right, and you can see my palm is up. So a positive charge would experience a force up. An electron is a negative charge, So it will experience a force down on our page. So down like so in the negative y direction. I'll even say like negative y direction. And again, why down? Because the right-hand rule is for positive charge. And so for a negative charge, you do your right-hand rule, and the direction of force would be at the back of your palm, so down. Finally, I think I can do C on this page. I think I gave myself some extra room. So let's do C. What would be the radius of the electron's circular path? So we've established that because the force is acting at an angle, 90-degree angle, perpendicular to V, that we're going to get some uniform circular motion. And so let's actually find that. So in our case, let's set up Newton's second law for circular motion. So what's providing the centripetal force? In this case, it's Fm. And we'll use v squared over r since we have information about the speed. And Fm from our work from earlier is equal to q times v times b. And sine theta is 1 because the angle is 90, equals mv squared over r. So these v's divide out. And if we rearrange, we get r equals m times v divided by q times b. And squeeze those in here. V was 4 times 10 to the 6. And 1.6 times 10 to the minus 19. And 0.2. Sorry, my dog is whining at me because I've locked her in the room with me. So I think we're just gonna barrel through and finish off this problem. Sorry if you guys can hear my dog whining. 4 times 10 to the 6. 1.6 10 to the minus 19 divided by 0.2. So I got 1.1 times 10 to the minus 4 meters. So that's like 0.1 of a millimeter. And so as this particle travels through, it's going to move in a circle, which is pretty cool. All right, so we've done an example finding the size of magnetic force. That's easy. It's just QVB sine theta. Just plug and play. You guys will need practice finding the direction and applying the right-hand rule. And it's okay if you got to dwell on this for a bit. If you haven't used the right-hand rule before, it does take some getting used to. We've looked at lots of examples. What's next? Well, now that we've talked about how to quantify the magnetic force, we actually can see how the mass of an electron was experimentally determined. And so that's what we'll do in our next lesson. It's going to be really fun. But until then, hope you guys are staying well. Have a great day, and we'll see you soon.